Firstly, a brief introduction. The abstract argumentation framework proposed by Dun is the core form for many applications in the field of argumentation. It considers the arguments and the attacks between them. Each internally consistent subset output by it is defined as an extension, and one type of extensions corresponds to one semantics. The framework and semantics constitute a complete argumentation system. Moreover, answer set programming, a declarative programming paradigm, is recognized as a powerful tool for knowledge representation and reasoning in argumentation framework. Based on the abstract argumentation framework, Carroll proposed the bipolar argumentation framework to include the support relations. Then the weighted bipolar argumentation framework is proposed, which considers the weights of arguments or relations. However, the various weighted bipolar argumentation frameworks and their variants proposed so far have some shortcomings. Some of them fail to comprehensively address additional information, and the others neglect to evaluate the acceptability of argument sets. However, in the practical context of case reasoning, it is customary to encounter a variety of elements, including deterministic evidence, uncertain testimonies, relations between them, as well as the associated credibility levels. This situation matches very well with the application scenario of weighted bipolar argumentation framework. The objective is to identify the complete and acceptable evidence chains through argumentation. This situation matches well with the extension semantics, which is mainly used to evaluate the acceptability of argument sets. Therefore, we propose a new weighted bipolar argumentation framework and its preferred semantics based on the principles of extension semantics. Moreover, we design and implement a reasoning tool based on answer set programming, and our objective is to process the additional information comprehensively, assess the acceptability of argument sets, and perform reasoning in weighted bipolar argumentation framework autonomously. Here we reach the second part, background knowledge. We begin with a concise review of the Dun's argumentation framework. A Dun argumentation framework is a pure F, including A and R. A means a finite set of arguments, and R means attacks between arguments. If there is AB belonging to R, we will say A attacks B. And if S attacks each B with BA belonging to R, we will say S defends B. The semantics of argumentation framework is defined as a function. For an argumentation framework, the set S is called a sigma extension of F. Several semantics have been proposed, such as grounded, complete, preferred. The preferred semantic can be regarded as the maximum set influence among the acceptable argument sets. The preferred semantics here is defined based on the admissible semantics. Then the bipolar argumentation framework is proposed to include the support relations. To achieve an equal treatment of the attacks and supports, we refer to the method proposed by PADL'. PADL' employs labelings to clarify the definition, which has been demonstrated to be equivalent to the extension approach. Labeling is a function which assigns a label to each argument, indicating accepted and undecided respectively. Then the deductive semantics can be defined here. A labeling L is deductive if it satisfies all these rules. Then the set S, including all the argument sets which are labeled yin, is deductive. Similar to the previous, we can define the preferred semantics based on the deductive semantics here. Then we reach the third part, the weighted bipolar argumentation framework we proposed in our study. A weighted bipolar argumentation framework is a tuple which takes into the weights of arguments and relations. To illustrate the semantics, I will introduce the definitions of violate and penalty here. For an argument A, if A does not belong to S, we say A is violated in the S. For a relation AB, if AB results in S failing to satisfy the deductive semantics in FBAF, we say AB is violated corresponding to S. Then the penalty of S in F can be defined as the sum of the weights of the violated arguments and the relations. We aim to minimize the value of penalty, so the definition of minimal penalty deductive can be defined here. A set S is minimal penalty deductive if there is no T such that penalty T is less than penalty S. Similar to the previous, we can define the preferred semantics based on the minimum penalty deductive semantics here. Then we compare the preferred semantics in the three frameworks from two distinct perspectives here. To facilitate the comprehension, we employ an example like this. It should be noted that elements that are not marked with numbers are considered to have a weight of 0. And alpha is used to represent the weight is positive infinite. On one hand, we weaken the weighted bipolar argumentation framework to argumentation framework and bipolar argumentation framework to evaluate the expressiveness. The preferred extensions in different frameworks are calculated as shown in the table. Intuitively, the preferred semantics in weighted bipolar argumentation framework considers more constraints, resulting in a more limited extension set. Then we can prove that when the minimum penalty in F is 0, the preferred extension set in F will be a subset of the preferred extension set in FBAF. However, this theorem does not necessarily hold for the AF scenario. Even if there are no attacks, the impact of support will also be taken into account in weighted bipolar argumentation framework, but this means all arguments will be accepted in argumentation framework. The preferred semantics in weighted bipolar argumentation framework can handle additional information on top of expressing and processing original information, showing better expressiveness. On the other hand, we strengthen the argumentation framework and the bipolar argumentation framework to weighted bipolar argumentation framework to evaluate the universality. The preferred extensions in different frameworks are calculated again, as shown in the table 2. By comparing table 1 and table 2, it can be seen that the preferred extensions of the both frameworks remain unchanged. Similarly, we can prove that if the deductive preferred extensions of the bipolar argumentation framework exist, the preferred extension set of the weighted bipolar argumentation framework will be equal to the preferred extension set of the bipolar argumentation framework. This equation does not necessarily hold for the argumentation framework scenario. And the fundamental reason is that deductive semantics has adjusted to treat attacks and supports equally, which changes the measurement of the attacks to some extent. To sum up, the preferred semantics in weighted bipolar argumentation framework encompasses the preferred semantics in bipolar argumentation framework, showing a degree of universality. In conclusion, its improvement of preferred semantics in bipolar argumentation framework is smooth, while its improvement of preferred semantics in argumentation framework is alternative. Then we apply our weighted bipolar argumentation framework to analyze part of the arbitral mode case. And the table summarizes the arguments, their source, and their relation from the case. Then we generate the appropriate weights to the arguments and the relations. We contend that the weight of arguments is mainly affected by its source, and the weight of relation depends mainly on the strength of the attack or support. Finally, we model the case as the corresponding weighted bipolar argumentation framework on the left. The result can be proved to be consistent with the conclusions in the original case. If we change the facts of the case, given the assumption that Sabrina and Sarah did not quarrel, the results will change accordingly. It is evident that the incorporation of additional information can exert a pivotal impact on the outcome of argumentation. And the weighted bipolar argumentation framework we propose here possesses the capability to accommodate this necessity and adjust the results accordingly. Here we comes the fourth part, implementation. To realize the automated reasoning in weighted bipolar argumentation framework, we implement a reasoning tool, ASPWBART. The implementation process can be divided into 4 steps, including representation, decomposition, transformation, solving, and search. Firstly, we design the representation of arguments and relations supported by ASPWBART like this. They denote respectively weighted arguments, weighted attacks, and weighted supports. ASPWBART aims to solving the preferred extensions in weighted bipolar argumentation framework, whose underlying semantics lies in deductive semantics. So we decompose the attack and support representations into. So we decompose the attack and support representations based on the deductive semantics. This rule represents the weight of the rule if argument A hurts, argument B does not hurt is W. The rest of the rules can be interpreted similarly. It should be noted that the decomposition rules are not directly expressible in ASP. So we need to transform the rules to a form supported by the ASP. Then the weak constraint is given here. Weak constraint is a special constraint rule in ASP, different from ordinary constraints in that the answer set cannot satisfy the weak constraints in the program. Here's its basic syntax. For an answer set X, the ASP solver will calculate the penalty of X at different levels according to the weak constraints violated by X, with a higher level penalty as small as possible to find the optimal answer sets. It is evident that the mechanism of weak constraints can be used to solve the minimum penalty deductive extensions. Here's already a method to convert a rule like this into the corresponding ASP program based on the weak constraints. The representations can be transformed into corresponding ASP programs through the previous steps, and the solving results will be minimum penalty deductive extensions. Based on this, we can search for the maximum set inclusions as the final results. Then we evaluate the efficiency of our reasoning tool. And here's the experimental environment configuration. Owing to the absence of standardized datasets in each experiment, we designed a fixed number of arguments and generate twice as many relations as arguments randomly. And the distribution between attacks and supports is determined at random. Here's the result. The result shows that the runtime is almost proportional to the total number of arguments and relations. The reasoning tool can find the results in seconds when the total number is on the scale of 100,000. And the tool can find the results in 1 minute when the scale is in the millions. But when the scale reaches higher, the reasoning tool needs a long time to solve the problem. It can be seen that ASPWBART can reach high solving efficiency under a certain problem scale. Here's the fifth part, concluding and future work. In concluding, we propose a new weighted bipolar argumentation framework, which enables a more diverse range of representations. And we propose the minimum penalty deductive preferred semantics, which considers attacks and supports equally and handles weights based on penalty. Finally, we implement the corresponding reasoning tool, which achieves the automated reasoning in weighted bipolar argumentation framework and has significant implications for practical research endeavors. There are still many areas that need to be improved. Firstly, there is no comprehensive study on the reasonable range and treatment on the weights between arguments and relations. So we will try to explore more appropriate ways to handle them. Secondly, the semantics proposed by us only makes smooth improvements on the deductive preferred semantics in bipolar argumentation framework. So we will try to apply refined adjustments in other semantic contexts. Thirdly, there is no standardized dataset, but several metro data
Hi, my question is regarding the weights. I guess, if I understood it well, that it's the user that decides the weights, right? So depending on the problem, you have to assign the weights. Is that true? I mean, it's not automatic, it's part of the model. Okay, so my question is, could be possible to learn these ways from a set of examples, for example, from some data set or something like that? I mean, because I think that deciding the value of these weights is critical, and I don't know if you have a particular methodology to assign the weights, or to check that these are the right weights, or to help the user decide the right ways, or to infer them from data, something in this direction? Have you considered?
Generate some weights objectively, and based on some standards like their sources, their credibility, their level of truth, and so on. And on the other hand, we plan to use the large language model to generate some weights, so we can measure between them and find better ways.
Okay. Okay, thank you.
So that question actually brought something to my mind that's more from the qualitative research area, is called inter-rater reliability. So if you're looking to generate weights, one thing you can do is, from a sample of people, see what the common consensus on a weight would be. Potentially that's more reliable than an LLM or something.
So I noticed that you are using Klingo for the implementation. So did you use any of the optimization functions provided by Klingo? Well, because you were trying to minimize the penalty or something, did you use any tools provided by Klingo, such as like optimization methods?